Hello, thanks for interest in our work. Here at NREL, we're trying to understand the species magnesium hydroxychloride. You probably know that in Gen 3 CSP, a big problem we face is corrosion of containment alloys when we're trying to use molten chloride salts. A lot of this corrosion is caused by the species magnesium hydroxychloride, which forms in the salts when they're exposed to moisture. You can see in the SEM figure on this poster some of the corrosion problems that can be caused by this species. We're working to better understand the species so that eventually we can design an electrochemical purification cell and remove the species. To begin, we found a way to form that magnesium hydroxide species in a controlled way so that we could study its properties. By doping salt melts with sodium hydroxide, we were able to form known concentrations of magnesium hydroxychloride. We used these salt melts in a specially designed electrochemical cell. This electrochemical cell has room for gas in, gas out, a thermocouple to monitor the temperature, a port through which salt can be extracted to study its composition by titrations, and 3 electrodes. One of these electrodes, the reference electrode, is simply there so that we can control the potential of the other 2 electrodes. The other 2 electrodes, the counter electrode and the working electrode, are where the interesting experiments are really happening. The working electrode is where negative potential is applied, causing the magnesium hydroxide species to turn into magnesium oxide, an inert solid species that will settle out of the salt melt. The counter electrode is made of magnesium, where the electrons flow from, causing magnesium 2+ to dissolve into solution. This completes the circuit between the electrodes, and it also keeps the salt composition stable, as the magnesium removed in the form of magnesium oxide is replaced by the magnesium from the counter electrode. This setup enables a number of interesting experiments. We can quantitatively assess the amount of magnesium hydroxychloride in solution by using cyclic voltammetry and analyzing peak current. We can therefore assess the diffusion of the species through the salt melt by performing rapid CV scans and using a number of other techniques. To date, we have achieved these steps. Currently, we're using the cell to try to understand not just the behavior, concentration, and diffusion of the magnesium hydroxychloride, but how it forms and how we can get rid of it. To understand how it forms, we're introducing a known amount of moisture into our containment cell by bubbling our inlet gas through salt water at a concentration with a known vapor pressure. So that head gas has a known amount of moisture, and we can use both titration of salt aliquots and our electrochemical setup to monitor the formation of magnesium hydroxychloride. This can be done with pure salt, or we can spike it with NaOH to have a starting non-zero concentration of magnesium hydroxychloride and see how that concentration evolves over time in the presence of moisture. We're also studying what happens when we apply a potential across the electrodes to remove that magnesium hydroxychloride. How long it takes is primarily based on the diffusion of the magnesium hydroxychloride, is what we're finding so far. Using these results, we're trying to provide an engineering design of an industrial scale purification unit based on the concept illustrated in the lab scale electrochemical cell shown above. Using properties of a molten salt, as well as the magnesium hydroxychloride data that we've gathered, we hope to provide a way to use electricity generated in situ in Gen 3 CSP plants to remove the corrosive magnesium hydroxychloride species and facilitate the successful implementation of Gen 3 CSP based on molten chloride salts. Thank you.